Good day, everyone. My name is Sakawibawa Dharma.
And my name is Julian Unggul
And today we are honored to present our research about bioplastic based on taro starch and orange peel pectin.
This research explores an eco-friendly plastic alternative derived from natural and biodegradable materials.
Plastic pollution is one of the most pressing environmental issues worldwide. Conventional petroleum-based plastics have contributed significantly to waste accumulation, taking centuries to degrade. Bioplastics have emerged as a promising solution, offering biodegradable alternatives that reduces environmental impact. In this study, we developed a bioplastic from taro starch and orange peel pectin, two abundant and renewable resources, aiming to evaluate its physical and mechanical properties.
Through this research, we aim to answer three key questions. First, what forms can emerge from the combination of taro starch and sweet orange peel pectin? Are there unique characteristics resulting from a simple extraction method? Second, what are the physical and mechanical properties of this bioplastic? And how well can it withstand stress conditions that may lead to degradation? But last but not least, what changes occur when the bioplastic is exposed to water? This study is designed to achieve the following objectives. First, to analyze the physical and mechanical properties of the produced bioplastic, including tensile strength, flexibility, and water resistance, to determine whether the bioplastic meets the necessary standards for practical application as a sustainable packaging alternative.
Now that we have established the objectives of this research, let's move on to the methodology. This section will be explained by step-by-step process of extracting pectin from sweet orange peels and using it to produce bioplastics. The first step is extracting pectin, a natural polysaccharide that helps improve the structural properties of bioplastics. To begin, we measure 100 grams of fresh sweet orange peels, cut them into small pieces, and wash them thoroughly to remove any impurities. The chopped peels are then boiled in 500 ml of distilled water with a pH adjusted to 1:3, using a few drops of 25% vinegar. This process, conducted at 80 to 90 Celsius for an hour, breaks down the cell walls, allowing pectin to dissolve into the solution. After boiling, the solution is filtered using a cloth or a 200 mesh sieve to remove solid residues. To isolate the pectin, we add 96% ethanol at a ratio of 2:1. For example, if the remaining filtrate is 100 ml, we add 200 ml of ethanol. This step separates the pectin from the acidic solution. The pectin precipitate is then filtered again using a 100 or 300 mesh sieve, dried and stored for use in bioplastic production. Now that we have extracted pectin, we can proceed to bioplastic production. This process involves mixing the extracted pectin with taro starch to form a biodegradable plastic alternative. In a 100 ml solution, we combine 20 grams of starch, 5 grams of extracted pectin, and 10 ml of glycerin. A small amount of vinegar is added to lower the pH, ensuring a more homogeneous mixture. The solution is continuously stirred and heated until it thickens and changes color. This helps enhance the polymerization process, improving the film-forming properties of the bioplastic. Once heated, the viscous mixture is poured into a flat mold and evenly spread. It is then left to dry under sunlight for 24 to 72 hours until a flexible bioplastic film forms. After drying, the bioplastic sheet is carefully removed and is now ready for further testing and evaluation.
We finally had to our results, and as you can see, there are 4 tables or 4 experiments in which we use small sheets of bioplastic, which comes to our first table, which is the water submersion experiment, in which we test if the sheet is resistant or soluble to water over a time period, which we have it at 0 hours, 2 hours, and 4 hours. This table shows the mass increase of the sheet after it is taken out of water. On the second table, we have the force experiment in which we tug on 3 sheets of bioplastic to see how much force is required to break the sheets, which results in an average of 1.53 newtons for each sheet. The third table shows the elongation of the sheets at an initial length of 3.5 centimeters and results at an average of 6.6 centimeters. The last table shows us the tensile strength, which requires us to find the cross-sectional area of the sheet and divide that by the force applied on the sheet, which results in an average of 0.1275 megapascals. So in conclusion, pectin acts as an adhesive in bioplastics, while starch functions as a thickener and binder. Starch gives the bioplastic a dark brown color due to oxidation, with visible brown spots from undissolved starch. Using local ingredients to extract pectin and taro starch supports local businesses and is a sustainable way of waste management. The resulting bioplastic passed several tests. After being soaked in water for 2 to 4 hours, their mass increased by 270.5% at 2 hours and 313.7% at 4 hours. Elongation test showed the bioplastic could stretch from 3.5 centimeters to about 6.5 centimeters. Tensile strength test revealed they could withstand a tensile force of 1.55 and give or take 3.5 newtons.